Hello and welcome to Maths on the Move, the podcast of plus.maths.org. I'm Marianne Freiberger.
And I'm Rachel Thomas. Marianne, have you ever made a mistake when you were doing your mathematics?
Well, what, me? No, never. Why?
Well, it turns out that mathematicians, unlike you, make mistakes all the time, even mathematicians who are better than you.
What do you mean, even in published papers?
Indeed, yeah, even in published papers. Some slip through this peer review process and the errors appear published in mathematical journals.
Oh, no.
I know, but it's okay, help is at hand. For some time now, mathematicians have been trying to enlist the help of computers. And I'm not talking about artificial intelligence here. I'm talking about something called proof assistants, which help check if a proof is correct.
Yes, I have heard of those. So basically, the proof assistant knows the axioms of maths on which everything is built, and it knows the rules of logic. And as long as you formulate a proof so that the proof assistant can read it, can understand it, it can check that everything can be deduced from the axioms using the rules of logic, just as it should.
Yeah, exactly. So these computer systems are taught the basic axioms and the rules of logic, and they only say it's true if these follow one from the other. And there was a pioneering program at the Isaac Newton Institute in 2017 called Big Proof, which looked at proof technology. And recently, this year, there was a follow-up program which included 3 Fields medalists.
Wow, okay.
I know. And together with our summer intern, Ben Watkins, we went to interview one of the program participants, Kevin Buzzard. He's an expert on the topic of proof assistants, and he uses a particular one called Lean. And he's involved with formalizing mathematical results, such as the famous result Fermat's last theorem, to make them suitable for such proof assistants.
Oh, the very famous Fermat's last theorem. Well, it's nice to meet you again.
We started out by asking Kevin what a proof assistant is.
Yeah, so a proof assistant, I guess it's a system that knows the axioms of mathematics and knows the rules of logic. And that's it. If you've got those 2 things, then you've probably got a proof assistant, but it might not be a very good one. So what do you have? It knows the axioms of maths, it knows the rules of logic. So what can you do with that? You could say, okay, so why don't we prove that 2 add 2 is 4? And then the system will probably say, well, what's 2? And then so now you realise the problem. Like it might know all the. It's like teaching somebody the rules of chess. You know, it's not suddenly a chess expert. You teach somebody the rules of maths, but now you've actually got to teach him, what mathematicians think about. So you've got to prove 2 add 2 is 4. So you have to say what 2 is, then you have to say what add is. You have to say what equals is, and then when you've said all those things, you can prove that 2 add 2 is 4.
So why would it be important to use proof assistants rather than, say, having a peer review your paper or check a proof is correct, would you say?
Well, the thing is, if you're playing chess against a chess computer, then you can't make an illegal move, right? I mean, it's pretty easy in chess to detect that your opponent has made an illegal move. But the problem is in maths, because maths is much more complicated than chess, we get papers published that have mistakes in. It's rare, and the mistakes are often not important, but sometimes there's a big howler. And the thing about doing maths in a proof assistant is that it sort of removes that possibility of making an error. So, it's not... Mathematicians have survived for thousands of years without using them, right? So the system does work without them, but it's just that, it's 2025, and now we can have that little extra... If we want it, we can have that extra edge.
I've also heard elsewhere that these proof checkers can help us speed up improving proofs, which seems quite counterintuitive from an outsider's perspective. Have you experienced that? Do you think this is...
They can make us think differently about proofs, but at the minute, on the whole, I would say it was probably not accurate to say that they're speeding us up. I would say that they're slowing us down right now. On average, they're slowing us down. They make us think differently. So they are doing some things. For example, we had, the lean community proved a theorem of Scholzer and Clausen a few years ago. And in the process of doing that, they thought exactly about what was needed, and they planned a route, and on the way, so as part of that planning, they were just like, well, we've got to use this really technical piece of machinery here. but that looks quite technical, so let's put it off. And then what do we need from this black box? And they figured out the things they needed, and then they realised that actually they didn't need all this technical machinery, which was in the original proof. So the proof did get simpler, because they were just like, oh, we can take lots of shortcuts here.
So it's forcing you to engage with the proof much more fundamentally.
Yeah,
perhaps, and that's where
it makes you read it line by line. And the moment you start reading a proof line by line very carefully and thinking about every line, then, again, maybe that's got nothing to do with the proof assistant, right? Maybe if you could persuade humans to read a proof very carefully line by line, they would find all the mistakes and they would find all the simplifications. But the thing is, it's very difficult to make somebody concentrate on something, for days and days and weeks and months. Whereas if you say type it into the computer, then suddenly you've got this fun part of it because it's turned it into a computer game. Oh, we're playing computer puzzle games suddenly, and also it's just very clear on what's done and what isn't done. It's very black and white. It's like, this is now under control, this is not under control. The computer is really explaining exactly what needs to be done. So it is helping people read proofs carefully, for sure.
Is this the feeling of when you're actually using proof assistance? Does it feel like a video game to you then?
Oh, for me, yeah. That's why I do it. This is my favourite computer game.
So Rachel, you have written about this idea of formalizing proofs before. So formalizing proofs means making them suitable for a proof assistant. And that was also following a workshop at the Newton Institute. And what struck me about that article that you wrote is that the endeavor of formalizing proofs seems to make mathematics much more collaborative.
Yes, that's right. This was last year in the workshop celebrating the 60th birthday of the mathematician Tim Gowers. And it was interesting because Tim Gowers has done lots of really innovative work about collaborative mathematics, famously this polymath project where he tried to get groups of mathematicians to work together online to solve mathematical problems. So the talk was by one of the program participants, Terence Tower, who's also a Fields medalist. And he was talking about recent work he'd done with Tim Gowers, proving a result. And as well as proving it in the traditional way, writing a mathematical paper, Terry Tower also formalized the proof into a way that could be understood by this software Lean. And the way you do that in a proof assistant is you set up what they call a dependency graph. This is the first stage of formalizing a proof, where you set, it's like a blueprint for the proof. So they knew how they did it in their mathematical paper, and they basically, each step in the mathematical proof was a bubble in this dependency graph, and it showed what previous parts of the proof it depended on, and it showed which of the next parts of the proof depended on that stage of the proof. And these bubbles in this dependency graph are color-coded. They're color-coded, I think it's into blue when they're formalized and they're ready to be proved in the proof assistant, and then they switch to green when they have been proved within this proof assistant model, when that's been actually formally checked by the proof assistant. And what's really fascinating about this way of doing mathematics is a whole team of people, I think it was about 30 in the end, who came together as a community online. They started proving these little bits of this large proof because they could just tackle one of the bubbles on this dependency graph. And Terry Tower had this lovely thing that he would wake up in the morning and be excited because he could see some of the bubbles had turned from like white to blue or blue to green, which meant that progress was happening across this way of proving. And it meant that some people could prove statements using Lean in one part of the dependency graph without having any of the mathematical expertise required in another section of the proof. So you really could sort of split up and share out the work of formalizing that proof within that mathematical community.
And when you and Ben went to talk to Kevin Buzzard, Ben also asked Kevin about this sort of collaborative way of proving something.
It's also fun to sometimes maths is considered quite an isolatory subject, My understanding of proof assistant projects is there's a large engagement from several people.
Yeah.
So is that more fun to do?
I think so.
Yeah.
I think before I got into this game, I think my largest collaborative paper was with like 3 co-authors, whereas I just ran a workshop last week in Oxford with 35 students, and me and another lecturer, and at the end we're going to have a 10-author paper at least, I think.
Oh, wow.
At the end of it, because we're going to teach a computer the very beginnings of the Langlands philosophy. This was somehow the big goal. And it's clear after this week in Oxford that it's going to happen, and we're a few weeks away from getting it over the line. But people are still even though the workshop's finished, people are still engaged because it's the summer, it's the perfect time. So me and a bunch of PhD students and this professor at UCL will end up writing a paper with 10 PhD students, which would be kind of cool, and a couple of undergraduates.
Awesome.
And a 16-year-old.
A 16-year-old as well?
Yeah. Some random 16-year-old showed up.
Clever kids.
Yeah.
So, Rachel, you and Ben saw Kevin Buzzard because of the Big Proof program, which took place this summer at the Newton Institute. But there was an original one, wasn't there, back in 2017?
Yes, that's right. And that was back in 2017 was just around the time that Kevin was first getting into the idea of using computers to help him with proofs. And we asked him about his involvement at that time. And
maybe we can talk then about how you got into it. You said, as we arrived, there was the 2017 program, the Isaac Newton Institute. Do you have memories of that and what got you into?
Well, I didn't go.
You didn't go?
No.
Oh, sorry.
The history was I was given Imperial's Intro to Proof class to teach in 2016, and the first year I taught it, I just copied what the guy had done the year before.
Was that a first year course?
Yeah, first year, first term.
I see. Okay.
First thing that the students see when they walk through the door. And then the second year I taught it, I thought, great, now I know what this course is all about. I'm going to mix it up and do some new stuff. And I thought, why don't I use computer theorem provers? Because they've been around for decades. And I thought, why don't I learn how to use a theorem prover, and then do some basic maths and show the students doing maths in a theorem. I thought that would be a cool thing to do with the undergraduates. And then 2 weeks after I'd had this idea and I was frantically learning how to use these systems, there was this conference that I was far too late to register for at the INI. But the INI were ahead of the game. They were live streaming. This is pre-COVID, right? This is 2017. They were already live streaming on the internet. So even though I couldn't register or go to the workshop, I could watch the talk. And I watched the first talk by Tom Hales. And he was using these same tools as me, but he was talking about the idea about using them to do modern research. And I'm just, I just spent 2 weeks proving the square root of 2 is irrational. And I'm looking at these slides thinking, wouldn't it be great to do advanced algebraic geometry in this system? Because clearly, what I'd realised very early on was that clearly the systems were capable, in theory, of doing whatever mathematics you like. They were just thinking pedantically and logically, and they worked. After 2 weeks, I'd come to the conclusion they clearly worked, and you could teach them anything, but they were being used by computer scientists for the most part, and so they knew nothing. There were loads and loads of basic undergraduate level results that had just never been checked in any of these proof assistants, because the computer scientists, they hadn't been to advanced undergraduate maths courses, right? They've been to computer science courses.
The status of the game now in terms of undergraduate is MathLib as well, all this?
Right, Lean's Maths Library, yeah. MathLib. It's got most of an undergraduate degree.
Okay.
Still not all. So I always go back to my undergraduate training and think, what did I learn as an undergraduate? And is it all there? And the two glaring holes at the minute, in my mind, it doesn't have derived cohomology, which is something I learned in third year manifolds. It's on the way, but it's not there. And it doesn't have Cauchy's integral formula. You can't integrate around a triangle. You can't integrate a holomorphic function around a triangle and prove that the answer is 0. You can integrate it around a rectangle, but not a triangle. So,
really?
Yeah. So you can prove lots of complex analysis because you can chop up a general area into small rectangles, which is like just as good as chopping up into small triangles.
Is there a bit of intuition as to why the triangle is harder than the rectangle?
No, it's just no one's got around to doing it.
Okay.
It's ridiculous. It's but yeah, so people need to do it. But so it definitely doesn't even know an undergraduate degree yet. But on the other hand, there's some areas of maths where it's at the boundary, right? Like Terry Tao's paper with Tim Gower's Green and Manners on the polynomial Feynman-Ruzhi conjecture.
Yeah.
It's this breakthrough result from 18 months ago, and the entire thing's been typed in.
I think Terence Tao said one thing he liked about the former proof checker was seeing this graph of the results slowly fill in with colours, and second, when they were doing it, they were able to take down the exponent from 12 to 11 from formalising the proof.
Wow, so not all university mathematics has been formalized yet. But some very cutting-edge results, like the polynomial Feynman-Ruzhi conjectures that was mentioned just now, they have been formalized.
That's right. That polynomial Feynman-Ruzhi conjecture is the one I mentioned earlier, where Terry Tao talked about proving that it was work he'd done with Tim Gowers.
Oh, okay.
So that really is very cutting-edge mathematics. But as Kevin said, the stuff that you would learn in an undergraduate course in mathematics still isn't all being formalized yet. But something that many of us are familiar with, undergrad or research mathematicians, is a very famous and still cutting-edge result, is Fermat's last theorem. Marianne, tell us a bit about that.
Oh, yes, the famous Fermat's last theorem. So to explain what it says, loads of people will have heard of Pythagoras' theorem. If you have a right-angled triangle, then and the sides are x, y, and z, then x squared plus y squared equals z squared. And there are plenty of instances where x, y, and z can be whole numbers. So if they are 3, 4, and 5, you get 3 squared is 9, plus 4 squared is 16, equals 25, which is 5 squared, right? Okay,
Yeah.
good. So what if, in this equation, the exponent is 2, because we have a squared. What if you change the exponent to be 3, 4, 5, 6, 7, 8, 9, any positive integer? Can you still find solutions x, y, z to this equation that are also whole numbers? That's Fermat's last theorem. And it was so tantalizing to mathematicians because Pierre de Fermat, after whom it's named, he wrote in the margin of a textbook that he had a marvelous proof for this fact that there are no integer solutions for exponents n bigger than 3 or equal to 3. And then people went like, oh, so what is that marvelous proof? And well, they couldn't find it for like 350 years. And when somebody finally did prove it, it was not an easy proof at all. It actually established a whole new area of mathematics. And the result was proved by somebody called Andrew Wiles. And we have interviews with him that we'll put in the show notes in podcast and article form, who finally proved the result and announced the proof at the Isaac Newton Institute. There was a little error in the proof, which took about a year to fix, and Wiles fixed it with the help of Richard Taylor. Now, there's a connection here to Kevin Buzzard, because Richard Taylor was Kevin Buzzard's PhD supervisor, and Andrew Wiles was Richard Taylor's PhD supervisor.
So Kevin Buzzard, who we're talking to in this podcast, is the academic grandchild of Andrew Wiles, who proved the Fermat's last theorem.
Exactly, that's right. So there is a connection.
And now Kevin is involved with formalizing this famous result, Fermat's last theorem. Here's Ben picking up the story.
So you were provided a 5-year grant by the EPSRC to formalize Fermat's last theorem.
Yeah.
Could we begin at, well, what is Fermat's last theorem? And what is your connection to it?
My advisor's advisor announced the proof in 93, and it was wrong, but then in joint work with my advisor, they fixed it up. My advisor cleared off to Princeton while I was a final year graduate student, so I had no advisor, but he was doing something important, so I forgave him. And by 1994 they had fixed it up, and all of a sudden this was like, suddenly number theory was hot news. There's been this big breakthrough, and this area of mathematics I've become an expert in, mod P modular forms, was suddenly flavour of the month, which was, as far as I was concerned, this was brilliant. So I then sailed into a nice postdoc in Berkeley with Ken Ribbett, one of the people that had, done this breakthrough intermediate work, and then sailed into this, a few years later. Yeah, then I generalised some of the work. Me and Taylor, generalised some of the work. We proved more. We didn't solve more equations. Wiles had a big idea. He proved an R equals T theorem, and then deduced Fermat's last theorem.
So when Andrew Wiles announced the proof of Fermat's last theorem, you were Andrew Wiles's
grand student. Yeah. That's right. I was also at the INI.
Yeah. Do you remember it being announced?
Well, he gave 3 lectures, and the first one I went to, and it was completely incomprehensible.
Oh, really?
And so I skipped the next 2.
Okay.
So you missed that, and I think I'll finish there.
Yeah. I wasn't there. I wasn't there at the third. In fact, I was on holiday with my girlfriend in Ireland. Because she had a week. She's a surgeon. She had a week off work. It was just like, great, this is our week. Let's go on holiday. And I was just like, yeah, but Fermat's last day. Because there was rumours that he was going to announce it. But I was also in love, so I went to we're still together, like 33 years later. So we went to Ireland instead. So I missed the third lecture. But I was at the first lecture, the unfashionable lecture that nobody. And the second lecture was all wrong anyway, right? It might have been the announcement, but it wasn't right. It wasn't right, So a year later, it was announced. Taylor came back from Princeton and gave a talk in Cambridge, and that was right. So so then we went on and proved more. We generalised it and simplified it and generalised it and proved more instances of the Langdon's philosophy, and I got some nice papers out of that.
Now, this work of Kevin's, which was building on Fermat's last theorem, it also illustrates what proof assistants are good at, doesn't it?
Yeah, that's right. So when building on Fermat's last theorem needs a result which Kevin's mentioned, Ken Ribbett has proved for all prime numbers greater than 2. So that's great, but there is the case of when the number is 2, and that's the only prime number that's even. But Ribbett had proved the result for all odd primes. So Kevin needed the same result, but this time he needed it to work for the prime number 2. So he had to painstakingly go through the original proof to see where it breaks if you replace an odd prime with the number 2. And so that's really, really tedious. But this is where proof assistants could really help in this kind of activity. Here's Kevin again.
And at some point we needed to generalise Ken Ribbett's paper from P is an odd prime to P is 2. And it was just a case of you delete this first sentence, then you've got to read the entire paper. And it's very slow. And all the references, every time, now we just use this reference. Now you've got to read the reference to see whether the reference, only works for P and odd prime. Because 2 is the weirdest prime, right? 2 is the only prime that isn't odd. And sometimes it's just a weird special case. So it took a long time to read this paper. And then conversely, when someone came along saying, they can beat Tau's result, they can change this 12 to an 11, you literally change the 12 to an 11, you recompile, and then the proof breaks in 10 places, and then you just fix those 10 places.
So that's the
it's just you can absolutely do it really, really efficiently. You can modify a proof. So, there's a very cool application.
Is there a reason why Fermat's last theorem is particularly interesting to put through a proof assistant rather than any other?
No. There's it's all sociological. Fermat's last theorem, for a start, that I'm not interested in Fermat's last theorem in some sense, right? Wiles introduced this new technique called, the R equals T theorem, and that just revolutionised mathematics. And 30 years later, people are still proving R equals T theorems. And what I wanted to make sure that Lean could understand R equals T theorems, and so how do I convince government to give me £1 million to have to buy out my teaching for 5 years. And you sell it with Fermat's last theorem because it was a hot topic. It was front page in the New York Times. It was like one of the biggest achievements in mathematics in the 20th century. But that's just a marketing thing. What I really want is to get proof assistants so they can understand modern mathematics in lots of areas. Right? Terry Tao's got it to the boundary of modern mathematics in his area, and I want it at the boundary of modern mathematics in my area. But the thing is, that's a much, much, much longer journey. Because the polynomial Feynman-Ricci conjecture, you can understand, you can explain that to a sixth former. Whereas the semi-stable Shimura-Taniyama conjecture, the thing that implied Fermat's last theorem, you need a master's degree to understand that. So this is the problem. We have to, there's lots of missing definitions. So I'm, teaching the system modern mathematical definitions, which are still being used today. Like Fermat's last theorem's 30 years old. That's the other thing. But we're teaching it ideas which are still being used today, and that's the real motivation, because I want language models to start reading Lean's maths library and then writing accurate mathematics, error-free mathematics, and coming up with new breakthroughs.
So here we are now, finally talking about artificial intelligence. I've been waiting for this. So will AI be doing interesting mathematics anytime soon?
Well, Ben asked Kevin just that question.
So the fantasy is that, just like computers are better than humans at chess, the fantasy is maybe computers get better than humans at maths, and then we could all retire early, or we could all start thinking about, finding new interesting questions. Instead of trying to answer questions, we can find new interesting questions and then get the computer to answer them all. So that's the fantasy. Mathematics is accelerated by a factor of 1,000. But that is a fantasy. It's science fiction at the minute. And while we're waiting to get to that fantasy, we could start thinking about how we're going to make mathematicians' lives better in general. And one of the things that mathematicians do that they constantly grumble about is refereeing papers. Because they've got to do two things. They've got to decide if the result's interesting, and they've got to decide whether the methods are actually strong enough to prove it. And if the system can plough through the details and say, well, here's the first mistake and here's the second mistake, and, then suddenly that's being super helpful to mathematicians, because then the mathematician can just, stick with making the value judgment, which is the fun part of the refereeing process.
Would I be right in saying that you're sceptical about how good large language models are at the moment at doing maths?
Well, at the moment, they're rubbish.
Yeah.
I mean, everyone says they're great, but, they're very limited in what they can do. They just got a gold medal in the IMO, so 2025 International Maths Olympiad. We've got 4 tech companies claiming a gold medal. But, I got a gold medal when I was 18. So, they're still... I got a perfect score when I was 18. I got 6 questions out of 6 right. They only got 5 out of 6. So I'm better than language models at the IMO, and this is, supposed to be a glorious success. And when it comes to research level stuff, the only research level questions that language models are dealing with are questions of what's this number? They're not coming out with research level proofs. They're coming out with one line. They're doing research level multiple choice questions basically, and that's not what research mathematics looks like. It's about finding long and difficult proofs. They're not ready yet. They might become ready, but they're not ready yet. And now the big question is, how are they going to get better? And there's currently people believe 2 different routes, right? Some people are saying we should just keep doing what we're doing, make them hallucinate less, give them more data, and eventually they'll just, read all the papers in this office, and eventually they'll be brilliant. But then my suggestion is actually, no, we should teach them formal languages and stop them hallucinating that way. So, who knows which way will win, but, I'm betting on the formal language side of things, because I just feel safer with machine. What I worry about is that in 5 years' time, the systems will be really good, and they'll be writing papers. If they're not wired up to Lean, they'll write a paper saying, here's a 100-page paper that proves the Birchman-Swinnerton-Dyer conjecture. And now that's made our lives worse, because now we've got to referee it, and it's written by a computer, and you know that these computers make things up, and if there's one thing in that paper that's made up, then the whole thing might come crashing to the ground, right? So that's what I worry, is that we're going to end up making things worse if we don't start plugging into formal. But if the thing says, I've got a proof of the Riemann hypothesis and it's all checked in Lean, then you're just like, great, that's a much higher level of trust I can put on that work.
So we did already mention the pioneering Big Proof program at the Newton Institute in 2017. There must have been some evolution since then.
Yes, things have really moved on since 2017, and that includes the participants who come to programs like this now. I asked Kevin what the initial program meant for him.
I started sending a lot of emails to Tom Hales, sort of asking where this was going and what the future was. And he had some big visionary ideas about getting a system which could understand the statements of modern mathematics, which is a million miles from where they were in 2017. Just getting a system that would understand the statements, and then forcing mathematicians or paying people to go through the top journals and just start teaching the computer the statements of what mathematicians believed. And I thought that's the start, because the proofs are hundreds of pages and would take an army to write down. But if we can teach the system the definitions, then Hales's ideas sounded brilliant to me, innovative and brilliant. And he applied for money from Sloan and got money, but then never did anything. I think COVID hit and sort of really disrupted things, and his ideas, his visionary ideas, somehow never saw the light of day, and they still, to a large extent, have not been fulfilled. In fact, I'm hiring 4 postdocs right now to do the thing that Hales said he would do in 2017.
And so they brought together.
They brought together computer scientists and there was very few mathematicians in the room. There was Tim Gowers, there was Tom Hales, there was Vladimir Voivodsky, who died 3 months later, and there was a room full of computer scientists. There was Jeremy Avigad, who works in the philosophy department, but he's got a degree in maths. He's got a PhD in logic. And there was a room full of computer scientists.
And they brought them together again recently in the
Big Proof 3.
And so what was that like? What was that workshop like as a chance to see the state of play in that community? So
I think one thing, it was Big Proof 3 and Big Proof 1 were very different. One, because language models didn't exist in Big Proof 1, there was a lot of people, talking about basic mathematics or trying to get computers, to think by themselves. But Big Proof 3, many of the talks were about Lean. Was never mentioned in Big Proof 1. Big Proof 3, many of the talks were about Lean, because this seems to have become the de facto system for doing mathematics. Because it's just, there's a community of mathematicians using it. And there were far more mathematicians in the room. That was the other big, which I think was a big win, really, because you have to have mathematicians involved. You can't just have computer scientists trying to figure out how to do modern research maths. You absolutely need to have the experts. And in some sense, Big Proof 1 failed to attract, it was just too weird at the time. This whole idea has become much more normalised now. Even though I say most mathematicians are not using AI in any, or they're not using Lean, they're not using language models, but it's clear now that they are aware of these things. I get fan mail from people saying, I don't do what you're doing, but I think that what you're doing is important, basically.
So is it coming of age?
Yeah, it's coming of age. So I&A were really ahead of the game with Big Proof 1, because they were saying this is something that might happen, and then it sort of happened now, and then Big Proof 3 was in some sense, oh look, let's run a conference on the same topic, and now look who's coming. Now we've got Terry Tao speaking, and Marina Viasovska speaking, and Tim Gowers. 3 Fields medalists spoke at this conference, and that's the weird. 3 Fields medalists who are experts in different areas of mathematics they're finding common ground. This is another thing. It's really, this WILES meeting that I missed. This is just full of experts in algebraic number theory. It's full of the same old people that you see at the same. For years afterwards, I would go to the conferences. It's the same old group of 25, 30 core people going to the same conferences. But Big Proof 3, you've got algebraists, analysts, topologists, computer scientists, people interested in AI, people from the tech companies. It's really, really broad and diverse. This is one thing that's quite exciting about the area now, is that it's actually a common ground where people from different disciplines can actually talk to each other.
So that was you, Rachel, and our brilliant summer intern, Ben Watkins, talking to Kevin Buzzard about proof assistance.
And we'll put links to anything that we've mentioned in the show notes for this episode, including a link to Ben's fantastic article on proof assistance and the Big Proof program.
And Ben also wrote a little walkthrough example of how to use Lean. So anybody who would like to have a go can look at that.
It's really fun to play with Lean. We strongly recommend it. So that's it for today's podcast. If you've enjoyed listening, please do consider recommending it to a friend, or you can rate or review the podcast wherever you're listening.
Thanks for listening, and bye for now.
Bye.